So good morning, everybody. It's a pleasure for me to introduce you Yoram Singer. Yoram was a professor at the Hebrew University of Jerusalem, and he was also a researcher in the AT&T research, and now he's a professor in the CS department in Princeton, at the same time leading 2 research groups in Google. Yoram did amazing work in online learning, and in fact, I consider him basically one of the most important researchers in this field. And I myself started working in this field, reading his papers. And I'm very excited today for his talk that will be about efficient preconditioning optimization for large-scale learning.
Thank you very much. Thanks for the introduction. Sorry for the late start. It's 8 a.m. for me. I just flew in from San Francisco, so thanks for the really kind introduction. I'm kind of, people say that they had a group. I am actually tailed to groups because everyone is smarter than me. So I'm fortunate to have 2 groups under the title Principles of Effective Machine Learning. The group in the East is co-led by Elad Hazan at Princeton. We announced the opening of the lab a few months ago, and there is a similar group that focuses on principles in Mountain View, the part of the Google Brain team. So since this work is mostly was done in Google, I'm not giving any credit to Princeton for this talk. So one thing about the talk itself, it kind of covers line of work of over 10 years, and it includes both practice and theory. I'm trying to make everything accessible, but if you see a couple of slides that are, say, theory focused, just bear with me if you don't have the background. I will, accompany all the, slides with also some motivation and experiments. And the experiments are, with real data that is available both in academia and at Google. Okay, so let me start with something that just to set the notation and something benign, and which is feed-forward networks. So my talk is mainly about optimization. But so for this reason, I'm going to abstract neural networks as just a function. So if we have a neural network, it is a mapping from input to output, where there are weights, and which I denote them as W1, W2, up to, in this case, there are 69 weights, but I wrote W70. So the network is just a mapping, a parametric mapping that depends on W. I can view it as a large vector. Later on, we will break the structure of W. Instead of just viewing it as a high-dimensional vector, we'll break it into its constituents. And the mapping takes an input X and outputs Y, where Y is typically a vector rather than a scalar. It can be the prediction, what class, what word we're going to see next, or what is the object class in the image. And as such, with training is just, we get a list of input target pairs. So these are the real targets. So for instance, what was the context up to a given word, and the target is the next word. And learning amounts to, from my sort of core perspective of someone who does machine learning, large-scale optimization for machine learning, learning is just trying to estimate the weight vector W such that the mapping of the network matches as often as possible the true targets. Clearly we cannot find a perfect matching, or at least in the past we could not find a perfect matching. These days in image categorization on the training data, we can actually find a perfect matching. But if you look at large-scale language problems like translation, we never find the correct word all the time. So in fact, the error rate can be in the more than 50%, of course, because at the dictionary of say 60,000 words, it's unlikely that we are always going to predict the next word correctly. So therefore, we cast a loss, and which sort of penalizes for the discrepancy between the mapping, the prediction of the network, and the true target. And this loss is we take it over all the examples. Now that I set the definition, basically what we have is just a function given the data that depends only on W. So now I abstracted the learning problem into an optimization problem. This is very common. But the advantage of this, the one particular part of this function is that it's a sum over examples. So I can even subsample and get an estimate of this function just by taking a subset, a random subset of these examples. But from now on, I can just talk about what does optimization entail. So my starting point will be convex optimization. And there is plenty of work in convex optimization. And here I just show a list of books. And in convex optimization, we're trying just to minimize a function f of w, which is convex. And w is a vector in our D. So the number of D is the number of parameters of, say, a network. So in the previous example, D would have been 69. And a common, so if this is our function, I'm not going to get into the definition of what is a convex function. But roughly speaking, a convex function means that every line connecting 2 points on the epigraph of the function goes above the function itself. And a common algorithm is a gradient-based algorithm that starts with some estimate. So it runs by iterations. It gets an estimate of the weights. It calculates the gradient. So the gradient is the derivative of element by element of the function. And given the gradient direction, it sort of makes a move. And the next point or the next estimate is called WT plus 1. And this process repeats itself. So typically, we do it in place so that we won't have to really save a sequence of weights. And so we take the current set of weights or parameters. We go in the direction of the gradient. And there is one thing here, which I call it PLR, or for pesky learning rate. This one, this is a scalar that tells you how much you should go in the direction of the gradient. And although it looks like just a single scalar, it's actually very important, and it can make a big difference of in terms of performance of algorithms, especially when we talk about billions of examples. Okay, so in fact, if I can summarize the entire talk would focus to from a very high level point of view at this really single scalar. Okay, so this is classical optimization. Now this is optimization 2019, right? We have you have a function, but now it's not convex, and we would like to get to a good point like this minimum. And what do? We just ignore the non-convexity. We start with a vector W, and then we make a step, and we get to WT plus 1. And then we say, oh, it works, right? Because we got to a better point. And the answer is no, but this is one of our biggest lies. We take the analysis that we do for convex optimization, and we hope that it locally holds for non-convex optimization. So I will keep lying during the entire talk. I will talk mostly using tools of convex optimization, but all of the experiments will be with deep networks. OK. So let me now recap, and I'm I will introduce notation. So gradient descent or stochastic gradient descent basically work in iterations. They take the current set of weights. They move in the direction of the gradient, where the gradient can be a full estimate of our objective, or just taking a subset of examples and creating an unbiased estimate of the function. Now, there are adaptive methods that were introduced over 10 years, almost 10 years ago, where instead of, and AdaGrad and Adam are one example. There is RMS prop. And in these methods, there is actually a private learning rate, a private step size. So if before the gradient was a vector whose dimension is the number of parameters, and you can think of, we think of vector or say, 3 dimensions, 100 dimensions. Think of G as billion dimensions or half a billion dimensions. And I'll show examples. Now we're going to have a private learning rate per entry of the weight vector. And the question is, OK, so what did we do? On one hand, we have a vector of dimension billion entries. We have a gradient of billion entries. And now suddenly we have also a learning rate per entry in the parameters, which is also a billion. We make the optimization process more difficult. And the answer is actually no. We can actually have, and we have algorithms which take linear time per step, and they became very effective. So where does this learning rate come from? Okay. So now I'm going to introduce, and then these slides are slightly mathematical. I'm going to actually give a picture in a second of what do we mean by learning rate. But think of the following. Suppose we go in the direction of the gradient. So think of going down. You want to do rim to rim in Grand Canyon, and you go down. So you typically walk and look at the steepest descent, and you go down. But actually, when you look at it, it's the canyon actually curves a little bit, the road down. So if you will just try to go down, but you will actually hit, the edges of this trail that goes down, and you will zigzag. So what preconditioning is telling you, your terrain doesn't look as nice. It doesn't look circular. And in order to actually accommodate this sort of twisted or non-uniform terrain, we multiply the gradient GT by a matrix, which I call here HD. It evolves with time. And for technical reasons, it's HT to the -1, which I'm going to explain. But again, so what did I do? I just introduced an even more difficult problem. If I have billion parameters, I have billion times billion matrix that I need to maintain. So what people do is they just use the diagonal of H. So if you look at these algorithms, grad descent, SGD, AdaGrad, Adam, and I'm going to explain one of them in sort of more details, what they do is they just say, let's ignore the entire matrix. Let's just look at the diagonal. There are, of course, classical methods and more modern methods in convex optimization, deterministic optimization, where people use the full matrix, Newton and quasi-Newton methods like LBFGS, full AdaGrad and natural gradient. They all use the full matrix. But this is not the case here. We will have to use a much more compact. But here's what preconditioning does. So this is my Grand Canyon, right? And this is a two-dimensional problem, just two parameters. But what you see here are the level curves of the function, meaning that here the circle or the ellipse at the inner ellipse is really the minimum. And if we do gradient descent, we will zigzag, because the gradient points us every time in the descent direction, and it will take us a lot of time, and we will bump wall to wall. If we say, let's try to stretch the space, and the stretching is done by this matrix HD, now suddenly we go almost directly to the optimum. So these are true runs, and I'm just plotting the intermediate points, but this is what preconditioning does. It makes your space look nicer, okay? It makes the world look spherical rather than twisted. So in practice, this preconditioning approach often yields much faster convergence and better estimate. We don't understand, but it's not only that we get faster to a good point, we also get often to a point where, or a set of parameters that also generalize better. They achieve better performance. So there are clearly obvious caveats. This approach with large matrix will require d cube in terms of running time. We'll have to take the inverse of the matrix. It will take also d squared space, which is prohibited. So in practice, only diagonal preconditioners are used. So what I'm going to do in this talk is actually talk about how can we cope with this large number of dimensions while being able to do some preconditioning. And the goal is actually to develop practical optimization for deep learning, which work well in practice. So the talk today will first talk about making full matrix preconditioning efficient and practical. And the second part is will go below the even linear space, and we'll eliminate the memory overhead. And this, I'll show you at the end, this will give not the state-of-the-art result. It's actually better than the state-of-the-art result. And I'll talk about some running time at the end. So what I drew on the left-hand side is this matrix HT, this big matrix HT. It's an illustration of a real matrix for a synthetic problem, low-dimensional problem. And so how do we go between the full matrix and the diagonal version? So what is drawn on the right is just the diagonal. So this, you can think of this as AdaGrad, Adam, whatever you like to use, whereas this is what theory tells us to use. So how do we sort of bridge this gap and, in fact, beat the diagonal case without increasing the memory and the runtime requirements? So what I'm going to talk about first is about Shampoo, which is efficient preconditioning. It is more expressive than diagonal. It will look into, when we go down, we need to say, oh, what is the correlation between east and west, between parameters? So it is more expressive than the diagonal version. And it is efficient, and it has nice convergence guarantees, and again, in the convex case. And it's easy to apply. It works well in practice. So now, after I dropped a lot of equations on you, let me go back and start again. And go back to my personal starting point, which was AdaGrad. It was actually, we first tried to publish it at ICML. It was rejected almost 10 years ago. We published it at Colt, and I think it's pretty well-respected algorithm. So what is AdaGrad? So suppose I'll give you the gradient along the run. So this is just a cartoonish view, a fictitious view. So G1, G2, assume that there are just 5 dimensions, and I give you the gradients along the run, and I say, these gradients are good. They will take you down. But the space itself is really twisted and rotated, and try to make it spherical again. Let's make the space great again. So what AdaGrad does in the full case, it takes the outer products of the gradients. What does it mean? It looks into correlations between every entry of the parameters as expressed through the gradient. And it creates this outer product matrix. So this is for G1, for G2, and this is along the run. And then it takes these outer products, sums them. So this is a sum over time, and take the root of it. So this is matrix root. Okay? So if you want to think what is the matrix root, because this matrix is symmetric and in fact PSD, you can do the spectral decomposition, and the root of the matrix would be the root of the eigenvalues of the matrix, and then multiply again. So this operation is well defined in matrix theory. And so this is what is the full AdaGrad. So the full AdaGrad will, every time, will update this matrix HT. And will take the inverse of it. Now, for the real experts in convex optimization, there is actually an explanation. Today, we know that there is an explanation that gives, sort of unifies many methods, like Newton and AdaGrad. So this explanation is written here. I'm not going to dive in, but if you want offline, come and talk to me. I'd be happy to discuss this. So the main problem distills into, okay, if we really want to take into account our space and we want to go down, how do we take the root of this big matrix? We need to make some concessions. So the idea is that if, again, we have, you can ignore the top picture. What we want to do, this is how we actually calculate the matrix, but what the yellow rectangle is what is important. We want to limit the domain. On one hand, we can do diagonal, which is easy. On the other hand, full matrix is difficult. So one option is to say, oh, let's assume that the matrix is full rank. Well, this doesn't help us much because the inverse is problematic. And also, we will need to keep factorizing the matrix. Or we can assume that it's sparse. Then again, the inverse is going to be dense. Or we can assume that it's sparse plus low rank. This is double trouble. And so on and so forth. Actually, a sketch version was, people work on that. And let's just project the gradient into a low-dimensional space and do the full matrix AdaGrad or the full matrix Adam in that space. There is no full matrix Adam, the full matrix AdaGrad. Okay. So what we search for is something practical that for which we have some guarantees by limiting the domain. So then we said, OK, convex optimization, great. But we really work with neural networks. Let's not ignore the structure of a network, right? So a neural network actually is, if you look even at the code, like the way parameters are saved for in PyTorch or TensorFlow, there are sort of, it's a list of tensors, right? So if we look at one layer in the network, it's a matrix actually. Why should we ignore the matrix structure? This is a fully connected layer, which maps, it's a linear transformation from one layer to another, followed by nonlinearity. We shouldn't ignore. And in fact, the gradient itself, because it's the derivatives of the parameters also form a matrix. So if we ignore it and try to make it into a big matrix, we're going to, again, have these 50,000 by 50,000 parameters. But if we are not going to ignore it, what we came up with is say, why don't we, for a second, ignore, sort of assume that we can preconditioning only from the left and precondition only from the right. So it's hard to take the example from going down a canyon. But suppose for a second, I'm going to look to the east and just try to say, OK, how much does the space to the east look like? And then I'm going to look to the north and just look at how much the curve, the space just looking north is going to look like. So Shampoo just says, oh, you have a structure. Let's just not ignore the structure and multiply this gradient matrix once from the left and once from the right. OK. So this construction, by the way, is not just useful in neural network. If we go back to the classical convex optimization, multi-class categorization, matrix completion, similarity learning, they all have this structure of employing at least one matrix. Okay? So it's actually a main primitive in modern ML, whether deep or shallow, convex or non-convex. So in fact, if we go back and look at the original equation, which again, I'm going to give a picture for it, what the limit is, we limit the space of preconditioners to Kronecker products. And instead of looking at the equation, so this is, let me actually explain what it is in a picture. So here is the original gradient matrix. This is the left preconditioner, and this is the right preconditioner. And this is the true preconditioner, the one that says, I'm going to look at north, east, and even up and down, and I'm going not to ignore the space. So the approximation that we do is we say, oh, let's, the preconditioning from the left and from the right is a Kronecker product, where a Kronecker product says, each rectangle here is of the size of the right matrix, but multiplied by the scalar LT that corresponds to the rectangle, the sub-rectangle in the matrix. So what we do, we actually work with this huge, virtually with this huge matrix by imposing a structure. So now this product of full matrix times the gradient as a vector is equal to multiplying by the inverse of the left preconditioner times the gradient, which is a matrix, times RT. And this is our now preconditioner. Yeah? Pardon? Nystrom. It's a good question. In order to use Nystrom, what we have here is actually a tight upper bound on preconditioning. And Nystrom would give you in expectation an approximation. But as you run, the variance of this approximation can grow. So we actually looked into it, including sketching, and we couldn't find an efficient way to develop an algorithm which is provably correct in the convex case. OK. So to summarize, what does Shampoo do? It doesn't ignore the network structure. It builds a left preconditioner, which is matrix-matrix products. It builds a right preconditioner. And you don't really need to remember the equation. And it has really nice convergence guarantees. Now, if we look at how does it work for neural network, our situation is even better, right? Because think of a convolutional neural network. Then a filter for an image as X and Y and input channels times output channels. So most constructs for vision models have four-dimensional or order 4 tensors. And now we can shampoo each dimension separately, and we can gain even more memory efficiency. And it amounts to this, again, for the experts, what we do is really we build a tight upper bound that depends on R is really the effective rank of the tensor. So I'll leave this. I'll do it offline if you're interested. But the end result is written here. So Shampoo is now open sourced. And if you go and look at the core, so although it makes a lot of matrix approximation, it takes 4 lines to implement it. So if you want a take-home message, preconditioning is good. Ignoring the network structure is bad. We can do much better. And it results in an efficient code. And we have some theoretical bound for it. OK. So wait. Neural networks are not convex. Why did I bother to do all of this math and algebra if neural networks are not convex? So this is, I sort of stated up front what is the big lie. We do the analysis and the design on the convex case. It's really my approach and our group approach is if something works in the convex case, then it might work in the non-convex case. But we start from a well-defined problem. So here was one of our first experiments. This is vision problem, which is continuous, and we didn't expect the Shampoo to work that well. And what you see here is a network called ResNet55. It has 55 layers. It has all sort of normalizations in the middle, and the task is CFAR100. So this is an image recognition data set where you get an image, and in the image there is an object that belongs to one of 100 classes: dolphin, shark, balloon, dog, cat. So we have 100 classes. So this problem by itself, just the top layer, is a large matrix of, say, the dimension of the output of the network times 100. And for these kind of problems, we see quite a bit of improvement. And so what do I show here? this is the number of iterations, large iterations, going once over the data. This is the loss that we optimize. And in terms of loss, we see really nice improvement. The blue line is classical SGD plus adding momentum, which actually improves SGD quite a bit. And we have the original AdaGrad in yellow. We have Adam in, in green. And this is Shampoo. And it takes only 5% more time for each iteration compared to SGD. So we got really nice improvement. Another problem, it's called the transformer. This is a very large-scale language model. Language model means that you take all the history of all the words that you've seen so far in a text, and you're trying to predict what is the next word. And your loss is the log of the probability of the prediction. And here, this is on test data. The y-axis is really what we're looking for. This is the log probability of a word. And again, you see this really nice improvement by preconditioning while not ignoring the network structure. So these successes made us think. So we take this gradient matrix, and we make a preconditioning from the left and preconditioning for the right. And this is the full Shampoo. Now the question is, there is a diagonal version of AdaGrad, or Adam is only diagonal. If we do this for the diagonal version, are we going to gain anything? So we thought that this is really not an epilogue, but an epitaph. What's the point in going below linear memory? So think of the diagonal case as just one big matrix whose dimension is the number of elements of the gradient. Why should we actually make this shampooing right and left with diagonal matrices? So here's this is the illustration. So if the diagonal AdaGrad or Adam require for, say, a tensor, two-dimensional tensor, which is a matrix, m times n memory elements, the diagonal Shampoo would require only m plus n. But what gives? Why, in what settings do we need it? So this actually let us think whether this is useful, and also, can it give us any improvements in any setting? Because we go below, we are sublinear in space. So then it's not difficult for us to look around, and this is when Ron Anil, who's a software engineer who's been working with us, pointed us to the sort of large models in machine translation. So what you see here is a set of models. Not all of them are published. One of them was done, the bottom one, by OpenAI. And you see in the middle column the number of parameters in the network. And on the right column, you see the number, the space that it requires. Now remember that in addition, this is the number of parameters. In addition to the number of parameters, we need to keep the gradient at least at each step. Now if we would like to do a preconditioning, even a diagonal one, we'll need to store another vector whose dimension is the dimension of the gradient. So now instead of, say, 5 gigabytes, we'll have to employ at least 16 gigabytes for just doing AdaGrad or Adam. Right? Now, what is the problem? In the current architectures, we use either GPUs or TPUs. We use processing units, which have limited memory. And the classical approach is to try to cram your learning algorithm into a single core of a TPU. Then you can distribute it, but every TPU or GPU maintains its own model, its own gradient, and makes update to the parameters. So this is really a problem if we would like to accelerate methods. And train them with preconditioned methods like AdaGrad and Adam. So now let's go back to our matrix. And clearly, preconditioning requires, twice the amount of memory for each element. So now we have a matrix. Each element is a cube in this matrix. It's a rectangle in this matrix. And even the diagonal version would require just matching element by element. So the issue is, or the observation that we had is that in neural networks, if you look at, say, all the weights going into a neuron, into a unit in the network, they often share same order of magnitudes, same statistics. The same goes for all the weights outgoing from one unit and spread into the next layer. They also share the same order of magnitude. So if we look at the structure and we look just at one column, this is, say, outgoing weights, or one column, incoming weights, they share the same magnitude. So what we did is say, OK, let's try to cover the set of parameters in terms of building preconditioners by finding a set of subsets. So each subset is subset of the parameters. And we're going to have an over-complete cover of the parameters, but it's over-complete, but still sublinear. So for example, in this case, we can take all the columns or all the rows, OK? And we're going to associate a single preconditioned parameter, a single learning rate per column and per row. So what we're going to do, we're going to take basically each column and each row, and we're going to associate a value which is the maximum of the gradient for that on a given iteration. And for each column, also the maximum. So we're now going to be conservative. If I say that I can go very fast in this direction, but very slow in that direction, I'll be conservative. In order to go in both directions, I will say, oh, let's use the slowest learning rate as my learning rate. Okay. So this algorithm is called SM3, and it's kind of a variation on an algorithm called X3 in multi-arm bandits. And what it does, let's go back here. What it does, it computes first the maximum for each column and for each row. Now, in a tensor, you can think about it as the maximum for each slice of the tensor, say x, y, input, output. And then it takes the minimum over the slices per element. So because we have an over-complete basis, we say, oh, you're conservative going there, you're conservative going there. But now we also have, say, the z dimension, and we're going to look at the z and x. And we're going to be conservative in each subspace, but we're going to be aggressive when we look at all the conservative estimates for the line. So this is SM3. And here's actually the pseudocode for it. So although it looks complicated, it's actually very simple to implement. Again, the Python code of SM3 is even simpler than Shampoo. I just want to mention that we're not the first to actually observe this issue with the need to have sublinear private learning rates or sublinear space preconditioning. And there are a few works on this problem, which are very interesting. This one came out of actually the Google AI group in Princeton, led by Elad Hazan. And there is also an algorithm that was developed just a few desks away from me by Noam Shazir and Stern, which used the same mechanism to reduce memory, and it actually was for a long time the de facto algorithm for using it. So here's again a very large problem. This is machine translation on English to German and English to French with two different models. One is called transformer. The other one is transformer big. Don't try to run it on your desktop. What you see here is the number of steps. We get to 1 million iterations. And on the y-axis is the log perplexity. And just a comment, if you used a popular approach like Adam, it became infeasible with the same batch size. We couldn't cram it into a single TPU core, therefore we couldn't parallelize it. And just to tell you what does 1 million iterations here mean, because these are large moles, it can amount to somewhere between a few weeks, if you're not careful, to a few days, like 3 days. So any improvement, which means that we melt less icebergs. We run all of the TPUs or GPUs for a shorter amount of time. And surprisingly, we also get better performance. So AdaFactor was published but developed internally at Google. And at the bottom, you see SM3, and you see significant improvement. Here's another example. This is called the BERT language mole. This is the largest mole for language modeling. It predicts the next word given all the previous words in the text. People say too that to a large extent it's a mix between memorization and real prediction generalization. But this is what we have to work with because it's so successful. It's used in question answering, for instance. And what you see here is, again, comparison of, now in this case, people used Adam to cram it into a TPU. And what you see here is the performance of SM3 out of the box. When you train these algorithms, often when you first turn in a new algorithm, you actually lose to the state of the art. And the reason is that the state of the art was tuned for a long time. But you see here, without tuning, we get significantly better performance by just increasing the batch size. And we can do it because our preconditioner is very tight in memory. Here's another example. This is a network called a MobaNet, which is a small network. So the question is, does it work on only large networks? So this network was found by a process called learning to learn by a group at Google, but it is published outside. So you can actually download or look at the definition of the network. And it was actually, when it was trained using an algorithm called RMS-prop by Jeffrey Hinton, who looked at AdaGrad and tried to understand it. It came with RMS-prop. So you need to bear in mind that the competitor here was actually particularly tuned for this problem. Nonetheless, we see again that SM3 outperforms the network. OK. So I'm going to conclude soon. So there is a remaining question, why Shampoo? So this is, I think it's taken from Corman. Shampoo is maybe the first computer science algorithm how to shampoo your hair. And there are a set of steps. But really, why Shampoo then? Well, it's because they made fun, my co-authors, of my hairstyle, because it's a preconditioner. You put first shampoo and then a preconditioner. All right. So here's a quick summary. I sort of try to give you a high-level view of memory-efficient regularization, illustrated, say, improvement in memory and computation. It is very practical, and it's by now used by several research and production teams at Google, including search. So every time you search, even if you searched 2 years ago, you somehow, your query probably got into the SM3 mechanism these days. And it's not just an internal preface. There is an open source TensorFlow implementation. A week after we put the paper on arXiv and the code in TensorFlow, someone implemented it in PyTorch. We looked at the implementation. It's perfect. It's correct. You're welcome to use it. I hope that someone will implement it in Julia. And we have plenty of theoretical open questions. So this domain of what is the gap between convex optimization to non-convex gradient-based search is sort of surfaces a lot of questions. We kind of sidestep them by working in the convex domain and applying it to the non-convex domain. So hopefully I gave you a taste of my particular approach, the approach that is developed in my group, that is both grounded in some theoretical considerations, but works well in practice, and by looking at real problems and trying to understand how we can accelerate learning. And accelerated learning these days means better generalization, because if you need to run something for 3 weeks and you have only 3 days, and you have a better algorithm that runs for 2 days, it means that you get the state of the art in far less energy and effort. Right. Thanks for listening.
All right, so at this time, we're going to open it up for questions. Any questions?
Pardon?
Are there any downsides of using SM3?
Oh, of course, of course.
Care to
Yeah,
expand on that a little bit?
absolutely. So suppose you want to do, say, sparse linear regression, and you have millions of parameters, but it's still linear regression. And the parameters form a matrix for that particular problem. So you want to do, say, either multi-valued regression. You can use SM3 because the problem is a structure, but you lose a lot, especially if you want to introduce sparsity promoting regularizers. Now there is a really odd interaction between the structure and the wish to have sparsity, and we lose big time. So there isn't one suit that fits everything. And we hit a sweet spot in terms of the size of the networks and the need to precondition. If you go back to classical convex optimization, matrix, even low-rank matrix factorization, we lose. And so it is tailored for problems where you know that preconditioning helps, but you don't have the space and the time to employ full preconditioning.
So you presented a lot of results on training loss going down faster than other methods, but you just presented one generalization case where it generalizes better. Does this happen in general, or is it just with big networks or small networks?
So in small networks, when you have sufficient amount of time to train, you don't see any gains. But when you need to train a machine translation model on so many sentence pairs, you typically don't go over the entire data sets more than a few times. So now the difference between training loss versus generalization is minuscule. There is actually almost no gap, and this is where we have big improvements. So as I said, if you want to train a small language, a small, say, vision model that's going to run on your phone, and you're going to have a network with, say, 1 million parameters, you don't need to use it. In fact, do the best you can, even a full matrix preconditioning, in order to cramp it. But all the examples that I gave, they translate to generalization because we really wanted to look at the very large models that take between days to weeks to train. Brian?
So there are some things that are known about gradient descent in non-convex settings, like under certain assumptions it'll hit a stationary point. So do you get any kind of guarantees like that when you do this kind of preconditioning?
So the short answer is no. The slightly longer answer is that I know of one work, it's not ours, on the convergence of AdaGrad to stationary points in the case of a 2-layer neural network. That's the best, that's the sort of the most non-convex setting that I'm aware of. And even the convergence guarantees are to a stationary point. They don't tell you whether this is a good stationary point.
All right, I think that's all the questions we have for today, so let's give a round of applause.